All right, thank you. Yeah, I guess I'm going back to the user perspective after Venkatesh. And I guess when it comes to the other new kid on the block, which is quantum computing, there's still not really established workflows. So what I will try to walk you through is more like a well-known chemistry problem, how we tackle it, and where do we foresee we can use quantum computing, because that hopefully triggers your imagination on how this can look in the future, right? But I'm not exist yet. So of course, we're still building hardware, software, and everything, right? So I mean, the workflow management, we're not even there because, well, we're still building the other pieces. Yeah, so let me just start. I mean, very simple. I mean, for a chemist here, I hope I say everything right. In chemistry in general, computational chemistry in particular, we are using models and simulations because we want to understand the structure, the properties, the reactivity of the molecules. Why do we want to do this? Because we want to either check the validity of some experimental results, be able to design new molecules, new materials, understand processes. For example, if you understand the reactivity of a certain process, maybe you can improve it, things like this, right? So it's a very important tool. And a chemist is probably one of the main users of HPC, or biochemist, condensed matter physicist. Very traditional community. They have been using HPCs for a long time, and they actually do workflows, even though it's not workflow management. But if I see the previous conversations about, what is a workflow? You have tasks, you have a sequence, like we're actually very good at it. So it's just that we do it manually, right? We always just say like, oh, then you have to do this, then you have to do that. And it's like a manual game constantly. So I'm going to try to tell you more or less what the problem is, or at least one of the issues. And for that, yeah, what is the problem? So how many atoms does an interesting molecule have? I mean, water is interesting, don't take me wrong, but not just one water molecule that's not so interesting. Normally you have a big molecule, right? So I'm going to try to think here about a protein. We're talking about really thousands of atoms, right? How small does this time step needs to be to ensure numerical simulation? If you want to sort of really see how the molecules are evolving, you need quite small time steps. Otherwise, the forces will just completely generate a numerical instability. How does that compare to the time scale of actually interesting biological processes, for example, right? And what is the level of theory needed to represent the process you want? Because in some cases, you might be okay with just, a continuum type of representation. But in some cases, if you want to actually see the reaction, that will not be enough. So this is the problem that chemists face. Let me just give you a very brief example. So this is a PYP protein. It's a photogel protein. It's involved in the response of a bacteria. So basically, when the blue light hits this protein, it creates a reaction where something gets protonated. I'm not going to go into details. Means that the charge in a specific pocket changes, and that makes the whole protein unfold. And this unfolding actually triggers the bacteria to run out away from the blue light. So it's super interesting. This protein has 125 amino acids. On average, each amino acid has 20 atoms. The process, the photocycle, is of the order of milliseconds. So let's assume we just represent the protein with balls and we evolve them in a Newtonian way. We need to calculate forces between 2,500 atoms, and that's not even taking into account the water or any solvent around it. We have a time step. I mean, here I put 1 nanosecond, but sometimes you actually need much smaller than that. And that already means millions of frames, right? And millions of frames where you're calculating all these forces constantly. So I guess with this in mind, you're not surprised they're big users of HPC. Now, how do we simulate these systems currently? There are different things. Obviously, specialized hardware is a big thing. Software has been optimized more and more. Usage of GPUs, really parallel programming, OpenMP, MPI, everything. We have a myriad of special techniques to accelerate the dynamics. This is actually a super interesting field, right? Like where you try to, like if you need to do a reaction that takes a long time, what you do is you try to bias the reaction, for example, by heating the system or by adding sort of energy potential biases that you take away afterwards. So there are a lot of really good techniques to accelerate the dynamics while still retrieving some physics out of it. You can do implicit solvents. So you basically say, okay, I won't care about the interactions with the water. I'm just going to take it as a continuum. You can do coarse graining, which means certain groups, you just treat them as bigger blobs, right? Many things that you can do to do this. But one of the problems is what happens when you're interested in phenomena across different timescales. And then what interests is something that we do a lot in especially biochemists, which is multi-scale modeling, which means that you couple different models and different levels of theory, and then you bridge between them. And one of them that I want to talk about is what we call QMMM. So it stands for quantum mechanics, molecular mechanics. And what you do is you have a reaction. So like in the PYP, there is a reaction that starts a whole cycle. You want to study the whole folding, but you also want to understand the reaction. So what you do is you just treat the small pocket of the reaction with quantum mechanics, and the rest you do it with molecular mechanics. And you basically do, as you see in the image, there is some sort of embedding, right? Molecular embedding. There are different ways that you can do this embedding. But I mean, basically, this is it. There is a lot of software that does this already automatically, these QMMM simulations. But you can also just think about it that you might have to coordinate two different softwares, right? So that you start triggering the workflow part. Now, this is a very sort of like a way of chemistry working, right? So we get our structure, we do some thermal equilibration, we check, well, we separate our pocket, quantum pocket, we thermalize again, we do some enhanced sampling to ensure. So this is more or less what chemists has been doing really for 30 years, if not more. But we do it very manually. So it's a good question to sort of understand how does this translate to workflows. Maybe just to say a couple of things. What happens in these QMMM steps is that you're constantly moving from one theory to the other. So you're computing the forces in the atoms, then taking those forces and sort of putting them in the quantum part as a mean force field, let's call it. And then you just go back and forward and back and forward. And depends which level of theory, you might be taking polarization effects or not. But this gives you an idea of what we're doing. All right. Question is, what is the level of theory you need for the quantum part if you want to study the reaction? And this has to do with the more accuracy you need, the more complicated the systems, the more expensive it is computationally as well, right? So you want to minimize the pocket that you need to really do in a different way, in a difficult way. And most of the methods that are, let's say, less expensive, they have a lot of trouble with what we call multi-reference states. So that's when you have electronic contributions coming from many different areas, strongly correlated states, transition metals, which are in enzymes, for example. Lots of issues with that, or it's very expensive to do it. And this is the part where I'm actually going to talk now about quantum computing, because one way that you can do this is that you can then, again, go one layer inside of the Matryoshka. And so you do molecular mechanics, then you do a pocket of quantum mechanics, and then you do yet another pocket of really like the hardcore, strongly correlated computations. And this part here, you could do it with traditional quantum software methods, but we could potentially also do it in the future with quantum computers. And this is one of the things that people are interested in doing. So this is a bit the idea, right? So we can exploit quantum computer to really calculate the strongly correlated pockets. Further than that, there is a couple of papers already exploring this, like given the size of the quantum computers we have now, can we even take that small pocket, this quantum computing pocket, and divide it in smaller pieces and then send the smaller pieces to actual quantum computers? I mean, this is just to trigger your imagination in how complicated this workflow is getting, right? Not only in terms of different software. When we start putting quantum computers on the game, it's also changing the type of information that we're moving, right? So, yeah, just to give you a bit of an idea, once you reach the quantum computer, one of the most well methods, I mean, there are two main methods that are expected to be used in, well, I'm going to call them family of methods. One is called phase estimation. The other one, which is more suitable right now, it's called variational quantum eigensolver. As the name says, variational is sort of like doing loops. So variational eigensolvers, what they do is basically they go from a quantum computer to compute, for example, the energy of the molecule, and then they optimize the parameters and so on, until you minimize energy. So again, this adds an extra layer of iterative processes. So as mentioned before by Elena, whenever you have iterations, this also complicates the workflows. So I guess we tick all the complications, right? It's conditional, sequential, parallel. So yeah, this is how we foresee using it. So basically what would happen in such a cycle is that you're running your normal, very traditional sort of QMMN simulations, but then the QM part, you suddenly substitute that for a quantum computing part, right? So that's how, at least the idea is being visualized in how to use quantum computers for chemistry. Again, I don't have a super nice picture of a workflow, but I hope that this triggers your imagination of the complexity of the workflow that we're thinking of. Yeah, that was it.